Sir, I would start by introducing you in the
Okay.
meeting. I welcome all the participants back for the 12th session of Faculty Development Program. I hope you had a refreshing break and are ready to dive into the next segment. So, for the 12th session, we have Dr. Virendra Vishwakarma, who will be sharing invaluable insights on artificial neural network and its advancements. Dr. Vishwakarma is a highly accomplished academician and researcher serving as a professor at the University of Information, Communication and Technology, GGSIPU. He holds a PhD degree in computer science and engineering from GGSIPU with a thesis focused on illumination invariant face recognition using fuzzy based feature extraction and SLFN classification. He earned his ME from MNIT Allahabad and BTech in Electrical Engineering from SBTI Kanpur, where he was a rank holder. With over 28 years of experience in academia and industry, Dr. Vishkarma has published more than 120 research papers, including 25 in SCI, SCIE Journal and 27 in Scopus Index journals. His Google Scholar profile highlights 1,280 citations, H index of 21, and an IT index of 45. His core strength areas include face recognitions, image processing, machine learning, and soft computing, digital watermarking. He has supervised eight completed PhD theses and currently guides six scholars working in machine learning, fuzzy techniques, and digital image processing. Dr. Vishkarma has successfully led multiple research projects, including those under the Faculty Research Grant Scheme, focusing on nonlinear feature extraction and fractional discrete cosine transformation for robust face recognition. His teaching expertise spans courses such as machine learning, digital image processing, and artificial intelligence. He has also been actively involved in curriculum development, PhD admissions, and other key academic responsibilities at GGSIPU, including roles in ACT, NIRF, and technical committees. In addition to teaching and research, Dr. Vishkarma has delivered numerous invited talks at national and international conferences and workshops addressing topics like soft computing, artificial neural networks, and digital image processing. He has contributed as a track chair, session chair, and technical reviewer at prestigious conferences and has been recognized with accolades such as Faculty Achievement Award 2019. His industrial experience includes Himachal Futuristic Communication Limited and the Research Design and Standard Organizations, where his contributions projects on electrical protection system and power supply optimization. I warmly welcome you on behalf of us all. Over to you, sir.
Thank you. Thank you, Deepali. So let me share my screen. Uh, hopefully this is visual.
Yes, sir.
Okay, fine. So today I will start with some basic concepts of artificial neural network. Some concept related to non-linear problem, backpropagation algorithm. What are the limitation of this? Then what are these solution methods like nonlinear modeling methods, CNN, etc. And if time permits, the application of all these to healthcare applications, healthcare problems, diagnosis, right? So obviously the audiences which are present here, I assume that they are familiar with the basic concepts of basic linear algebra, mathematics. Even if they are not very much familiar, no problem. They can understand the basic concepts if you have interest, definitely. So why we are going to study about artificial neural network very first? So basic question that although we are having a very high computation power in our daily handheld devices, mobile laptops, and lot of memory storage capacity, even though we are tending towards the modeling of what the way our human brain works. And that is the origination of artificial neural network. And this fascinated the researchers in various domains of mathematics, engineering, not only from the early 90s. It continues till the evolution of semiconductor revolution. And after having high computation power in the era of this 20th century, with GPUs, etc. Uh, Now we are aiming towards the more complicated problems to be solved with the help of some new models like deep learning models, LSTM, etc., etc. But basic concepts behind all this actually uh, can mimic whatever the human brain power, uh, not in a very impressive way of implementation. It's basically a very simple implementation of human behavior, human thinking. And that's why we say that artificial neural networks are very crude attempt to model the highly massive parallel processing which we can think it's happening in our brain. So if you go to the basic definition that this definition given by Simon Hacking, one of the very renowned researcher in this particular domain. So it's a saying that the neural network is massively parallel distributed processors made up of simple processing units, which has a natural propensity for storing experimental knowledge and making it available for use. So in this particular model, we are representing human brain into main resembling one particular where the knowledge, what the way knowledge is acquired, and that we say that this is the learning process. So acquiring the knowledge, that is the learning process, and from where we acquire the knowledge, from the environment. How we acquire the knowledge? Through its sensory organs. As human brain, we are having sensory organs. So similarly, the artificial neural network having some inputs, and they are supposed to be the data taken from the outside world. So when we talk about the study of artificial neural network, mainly we are talking about it's algorithmic concepts, how the informations are being processed, what the way information being stored, and what are their basically the interconnection models, etc. Right? So if the complete study of artificial neural network, if we say that it's having basically three components. One is the neuron model, what way the artificial neuron resembles the biological neuron. So basically, biological neuron is supposed to be a very simple processing element which is getting some input and then some non-linear or linear processing happening, and that is giving as a output to the axon. That is the biological neuron. So similar model we supposed to have in the neuron, artificial neuron, and that is basically the modeling of simple processing elements. So complete processing happening is a one particular element which we call the artificial neuron. What mathematical model basically, that is a just after a few slides I will tell you that this is a very simple multiplication of some variables, some vectors, and that is being processed by some functions, and that is the output of the neuron. So not only this neuron, there are the multiple number of neurons, and what they are interconnected, that we call the architecture of the neurons, right? So architecture means what the way the one particular neuron is interlinked to the other neuron. If I give you a brief just approximate idea what the way human brain neurons are interconnected and what is the order of the neurons, biological neurons in our human brain. So it's a basically approximation that it's approximately 10 to the power 14 to 15 number of biological neurons present in our human brain, and it is having an order of interconnection with one neuron to another neuron. It's order of 10 power 10 to 10 power 11 approximately, although these are just approximations. No one has seen a working human brain. So the approximations has been obtained from various studies like EEG analysis, biological, psychological surveys, etc., etc. So in this particular talk, I will mainly focus uh, the architecture, the learning algorithm, right? Learning algorithm means what the way the information being acquired and processed. So basically the information, where the information are stored in human brain, just interconnection strength synaptic weights, which we call. So similarly, in artificial neural networks also, we name a word synaptic weight, or simply weights which are having the interconnection strength between different neurons, and information is being stored there. So when we say a learning process, learning algorithm, that is the learning algorithm means that what the way these synaptic weights and biases obviously are being modified. So the complete learning algorithm can, if we talk about the categorization of learning algorithm, there are basically three types of learning algorithms. One is supervised, unsupervised, and reinforcement layer. So when we say that supervised, that means we are having some sort of input corresponding their output. They, in that general terminology, we call it the label data. So label data, that means it is having some set of input corresponding labels, or the target or the classes has been defined, right? And when we talk about the unsupervised learning, there is no desired task, classes, or the label has been given. Only the input is given, and based on the association or the uh, similarity between the inputs, it is clustered between different categories. And the third one, that is the reinforcement learning. So that is the learning uh, based on the event processing, that is the in a particular environment, what the way one particular agent, say for example, is interacting with the environment, and what are the possible state actions. Based on that actions, it is doing new, it is getting new state, and different states with the help of actions are getting some rewards or some negative signals. So based objective of the reinforcement learning is to maximize the total reward. So mostly being applied in nowadays for robotics and game playing. Although reinforcement learning has been modified in some sort to apply for pattern classifications also. But still, when we talk about the learning algorithm, we mainly focus on supervised and unsupervised learning. So when we say that it is having a learning and supervised, that means it is having a particular training set. So on the training set, obviously the neural network has learned very well, but what is the performance of the neural network on unseen data? Means what is the performance on the data which has not been used for the training purpose? So that we say that the generalization performance. The generalization performance good if neural network has been trained appropriately, and there are two conditions, two very uh, signifying terminology being used. One is underfitting and overfitting. So appropriate learning means the neural network has not been undergone underfitting or overfitting. It is appropriately trained, and for a given problem, it is for unseen data, it is doing good generalization performance on unseen data, right? So let us go in a deeper more. So this particular slide show you this particular component is the biological neuron, and in this particular, it is having approximately 10 to the power 14 to 15 number of such type of neurons which are highly interconnected. So this particular neuron is simulated one processing element as a artificial neuron in the what you call artificial neural network terminology. And we are having a very systematic type of interconnections, like we can have a fully connected feed forward neural network, single, say for example, single processing layer. So this particular component will not be there, it's only one particular processing layer. So that sort of architectures. So this particular slide tell you some comparison between biological processing system, that is the human brain, and the artificial neural network. So in terms of speed, what the way the processing happening in our human brain, it's order of few milliseconds, whereas in artificial neural network, depending on the processor being used, so gigahertz processor, obviously the processing happening in the nanosecond. Size and complexity, the obviously in a biological neuron, very high degree of very high interconnected massive parallel processing system is there. Complexity has not yet been very well implemented so far, and it depends in artificial neural network what type of architecture being used depending on the problem scenario. Storage capacity, human brain uh, not being fully utilized what the human brain capacity so far. And here, obviously, it depends upon the architecture, what the contiguous memory locations or what type of implementation happening. Say, for example, in associative memory, one application of neural network for association between different data. So that type of interconnections are storing the information, and which we call associative memory. Although that is also a two type: auto-associative, hetero-associative memories, right? In fact, the study of neural network having a very wider domains. So this particular talk, I am mainly focusing on some fundamental concepts, right? Now, this last one, the control mechanism. If we talk about the control mechanism happening in the human brain, that is a very complicated processing happening in our human brain, which is not yet been completely simulated in artificial neural network. Still, we are using a variant of back propagation, which I'll tell you after a few slides. So back propagation was the algorithm being developed in the era of 1980, and still we are using some variants of the back propagation. 1985, Rosenblatt has given this steepest descent back propagation algorithm. So this particular domain of the research is very open, and where the researchers can think of what type of newer learning algorithms can be developed, right? So let us go further. So this slide shows you a very simple representation of artificial neuron. So if you look carefully, x1, x2, x3, these are the inputs. So input is n dimensional. We say that the dimension of the input is n, and each input is connected by a synaptic weight. So the number of synaptic weights for a single neuron is obviously the number of the neurons, number of interconnection synaptic weights are n, depending on the size of the input. And how it is getting the output, why, that is depending on an activation function and how this is being processed. So this is basically the inner product of synaptic weights and the input. So inner product in the sense that if it is represented as a vector, W vector, synaptic weight vector of n dimensional vector, and X is also a vector of n dimension. So the net input is basically the inner product, dot product of these two vectors. Or in a simple way, it can be represented as sigma of I is equal to 1 to n wi xi. So all w1 multiplied by x1 plus w2 x2 w3 x3 and so on wn xn. So that is vk. That is the kth neuron net input. Okay, and on this we apply some activation function represented by phi. So that is the output y. So y is basically phi of vk. And what is vk? Vk is the net input, which is the summation of uh, product of synaptic weight and input, right? This is not only the one particular model. There are even more models. Some I will discuss. So this is one of the most commonly used model of the artificial neural network. Although it's very simple, but for many of the problem, it can be used to solve the problem efficiently. I was talking about an activation function phi. So what type of activation functions are there? So the total activation functions can be categorized in three: threshold, linear, and sigmoid. So threshold means this particular shape is representing the threshold activation function. If Vk is greater than or equal to 0, output y is equal to 1. So this particular y is equal to 1, right? So sometimes we call it step function or unit step function. because the output is 1 for v greater than or equal to 0, and v is less than 0, this is equal to 0. So this is a unipolar threshold activation function. Its a variant is basically bipolar. When we categorize the output in representation by 1 and -1, we mean the yk to be 1 or -1. So this is simply the same as the unipolar. V is greater than or equal to 0, phi of v is equal to 1, and v less than 0, phi of v is equal to -1. So that is a bipolar representation, right? This type of neurons were used with this activation function first by 1943 even by McCullough-Pitts, and by them it was named the McCullough-Pitt model. Uh, these are used for analysis purpose, analytical analysis, not this having some limitation, which I will tell you later, that for multi-layer feed-forward neural network, it cannot be used at hidden layer, but it can be used at output layer. And single layer feed forward neural network, it can be used at output layer. Linear activation function, whatever this v, that is equal to y. So linear activation functions are again of multiple subdivisions like rectified linear unit, saturated linear, bipolar saturated linear, and many more. The third category is sigmoidal activation functions. Sigmoidal activation functions are one of the most uh, commonly used and important for many of the classification problem, and it is represented by 1 upon 1 plus e power minus av. If a is equal to 1, so that is basically 1 upon 1 plus e power minus v. So a is basically the slope parameter controlling the slope of the activation function. If a is equal to 1, the slope at 0.5 is equal to 1. Okay. And if a is increasing positive value, a more than 1, say for example 1.5, so this particular. If a is very high, it is very similar to the threshold activation function. And if a is very small, it is very similar to the linear activation function, right? By default in sigmoidal activation function, the value of a is used as 1. Just like others, bipolar and unipolar component, sigmoidal also having two variants. This particular, the diagram, the slide which I'm showing is basically representing the log sigmoidal activation function, right? And uh, it's a bipolar variant named as tan sigmoidal. Tan sigmoidal, the equation is similar to this, but it is 1 minus e power minus v upon 1 plus e power minus v. The output is varying between -1 to 1 asymptotically, right? When we talk about the architecture, so the architecture of neural network, broad division, single layer feed forward neural network, multi-layer feed forward neural network, and recurrent neural network. So what is the meaning of single layer? There is only one processing layer, one input layer, one output layer, and only the processing layer is the output layer. So that is why the name is single layer feed forward neural network. What type of processing happening? It is summation of the inner product of synaptic weights vector and input vector at each neuron, and then an activation function, right? When we stack them, this particular layer stacked just after this another, and these outputs are feed forward to all the neurons in same way as it was done, fully connected manner. So there is another processing layer. So that is the variant which we call multi-layer feed forward neural network. So in multi-layer feed forward neural network, there is at least one hidden layer, which is in between input layer and output layer, right? So one hidden layer and one output layer, obviously one input layer. So this type of structure is known as multi-layer feed forward neural network. And it is further divided into shallow multi-layer feed-forward neural network and deep neural network. If there are more than 2 hidden layers, we categorize them deep neural network. And if there is only one hidden layer or 2 hidden layers, that is categorized as shallow multi-layer feed-forward neural network. Why we need a hidden layer? Why it is not sufficient to work with a single layer? Anyone? Any idea? Any audience? Okay. The The problem of the single layer feed forward neural network, I'll show you by one example, that this is a one simple representation of single layer feed forward neural network, in which there is only simplified form. There is only one neuron, which is a representation of the one layer, one processing layer. And X1 and X2 is basically the representation of the input layer. So there is one processing layer, this particular layer, and having the output O. So this is a simplest representation of single layer feed forward neural network. And this I am showing you because the output O can be obtained by V over the threshold activation function. V as an input to the threshold activation function. So what is the value of V? If V is equal to 0, output O or Y is equal to 1, and V greater than 0, output is equal to 1. V less than 0, output is equal to 0. So at V is equal to 0, we call the equation as a decision line equation. So what is the equation of decision line? That is equal to x1 plus x2 minus 1.5. And if I include in place of 1 and 1, it is basically W1. So that is W1x1 plus W2x2 plus B is equal to 0. That is the general equation of decision line. And if we look carefully at this equation, this is the basically linear equation in the form of y is equal to mx plus c, where y is equal to x2 and x is equal to x1. So linear equation, there is no power more than 1. So the equation of this particular is a line equation, right? There is a special case when W1 is equal to 1 and W2 is equal to 1. So this particular line can be used to categorize a problem of AND gate, simulation of AND gate. AND gate means all the input are 1, then only output is 1, otherwise the output is 0. So corresponding to 0, 0, this is the input space, x1 and x2 as a axis. So x1 is 0, x2 is 0, that is the origin, and that is having output 0. This particular is 1 comma 0, x1 is 1 and x2 is equal to 0. So output is equal to 0. And the third one, this is 0, 1, output is 0. Only x1 is 1 and x2 is 1, output is 1. And this can be categorized in two categories having output 1, and this is the output 0. So the output are categorized in two categories by this decision line, which is an equation of a line. So that is why this particular problem is termed as linear problem. So AND, OR, NAND, NOR, these are the problems categorized into linear problems. Whereas XOR, XNOR are non-linear problems. Can we solve with the help of this decision line non-linear problem? No, we cannot solve a non-linear problem. And to solve a non-linear problem, we need at least one hidden layer. Okay, so that is why the need of multi-layer feed-forward neural network. And in fact, all the problems of classification, pattern recognition in real world are non-linear in the nature. Like any pattern recognition, face recognition, gait recognition, fingerprint recognition, uh, iris recognition, any image classification task, share market prediction, weather forecasting, all these are non-linear in the nature. And that cannot be solved with the help of a single layer feed-forward neural network. We need multi-layer feed-forward neural network. Okay. What is the learning algorithm for see, for this particular problem, which is I am representing here in this slide, AND gets problem. So AND get with two input can be analyzed very easily in two-dimensional space, and we can find out what could be the value of W1, W2, and B by finding the equation of this particular line. Okay. But if the dimension of input increasing more than 3, it cannot be analyzed in this way. We need some learning algorithm. Or if this is a very simple problem and this type of classification analytical method will not work. So for more dimension of the input, we need some learning algorithm even for single layer feed forward neural network. And for single layer feed forward neural network, we have one learning algorithm which we call perceptron learning algorithm. So perceptron learning algorithm is basically used for single layer feed forward neural network, right? Which is for solution of linear problem. So for linear problem, perceptron learning algorithm will converge in finite number of iteration. And if problem is non-linear, it will not converge. So converge means it will get the desired values of weights and biases in finite number of iteration to classify problem accurately, right? But for multi-layer or for non-linear problem, because we for non-linear problem, we need a multi-layer feed-forward neural network. We cannot apply perceptron learning algorithm. So for that, we need another learning algorithm that is called backpropagation algorithm. Now, next slide, I will show you this particular is again our problem, which is a linear in the nature, and this particular decision line that is x1 plus x2 minus 0.5 is able to classify this. Now, this particular slide, I am trying to explain you that how this non-linear problem can be solved with the help of addition of one hidden layer. So this is a representation of this is the representation of a hidden layer. Okay. So this non-linear problem is decomposed into multiple linear problems. And this decomposition of the non-linear problem into linear problems can be done easily analytically in two-dimensional space, like this particular way. Okay, I will explain. But for high dimensional problem or more number of layers, or the problem complicated, not binary multi-valued problem, x1 and x2 are having more number of value, or x1, x2, x3 up to xn, we need some learning algorithm. And that the learning algorithm, I will tell you the steepest descent backpropagation algorithm. But before that, let us understand how this non-linear problem has been decomposed into multiple linear problems, right? The concepts are you able to understand the concepts which I am telling? Hopefully. If any problem, please. Okay. So how this is decomposed into multiple linear problems. So let us see in two-dimensional input space, x1 on the x-axis, x2 on the second axis. When x1 and x2 are 0, 0, output is 0. And when x1 and x2 are 1, 1, output is 0. For 0, 1 and 1, 0, output is 1. That is the XOR. So if I draw a line here, on this side output is 1, but on this side both output 1 and 0. On this side output is 0, right? This side both are. So that is not the correct classification. Similarly, if I draw a decision line here, again the same problem, 1, 1 and 0. So this is not the correct classification. So how this is happening and how this is solved into multiple linear problems? Let us design this particular neuron. This is the representation of the summation, that is it is doing the summation of what? W11 multiplied by x1, W12 multiplied by x2, right? Plus B1. So this particular, let us work as a AND gate. So AND get, that means for 1 1 it is having the output 1, and for all other 3 points it is having output 0, right? Fine. Now on this particular, if I draw this particular is 0 0 0 and 1, right? For these 3 observations the output are 0 0, and for the last one output is 1, that is the AND gate. Similarly, I am having for the second neuron of the hidden layer 0 1 1 1, that is working as an OR gate. That is for 0 1 1 0 and 1 1 output is 1, and for 0 0 output is 0. Now we are combining the output of these two neurons by a third neuron in the output layer, right? So how this is combined? We are inverting the output of the first neuron of the hidden layer. So by inversion means 1 is multiplied by -2. This becomes -2, and rest 0 0 0 0 0 0 0 multiplied by -2 obviously becomes 0. So the third neuron, how it is behaving, the output for the 1 1 is -2 by multiplying by -2, and this particular multiplied by 1. So 0 1 1 1, that is the output from the second neuron after multiplication by its synaptic weight. Adding a bias minus 0.5. So summed value is basically, here it is minus 0.5, and for these two plus 0.5, and for third one because of -2 it is negative. So because of this negative it is having output 0 corresponding to 1 1, and that is the way we want to work. So the non-linear problem is divided into 3 linear problems. One linear problem solved by the first neuron of the hidden layer, second linear problem solved by the second neuron of the hidden layer, and what are the output of these two neurons are again classified linearly by the third neuron. So we can understand that this particular neuron, this particular layer is able to convert a non-linear problem into linear in the hidden space, in the space of hidden layer, right? So that is the need for hidden layer, and that is the way the hidden layer works. So it's trying to map a input space into the hidden space, which is linear, non-linear, probably not always guaranteed, but it is a assumption that the problem may be linear in the hidden space. If it is not hidden layer, we can do further processing with the multiple number of hidden layers, and that is the need. That is the basically driven, what you call, uh, direction for research for the multiple hidden layers, and that is basically the deep neural networks, right? So now let me, this is another way of solving the same problem, again decomposing into 3 linear problems. So now the multi-layer feed forward neural network, for any high dimensional input problem or any generic problem, when input is varying not only binary, it is having multiple values, what the learning algorithm can be, and that is the learning algorithm which we call steepest descent backpropagation. And why the name backpropagation? Because the error is propagated in the backward direction. So it is using the sigmoidal activation function at hidden layer. And why we need sigmoidal activation function at hidden layer? Because it is not completely filtering the information at hidden layer by the threshold activation function. If we see the working of the threshold activation function filters completely whatever the variations in the input data. If we apply hidden layer activation function as a threshold, it will filter out. And if we apply pure linear, again there is no a non-linear transformation. So at hidden layer in the conventional neural network, feed forward neural network, they are having log sigmoid or tan sigmoidal activation function at the hidden layers, right? So in steepest descent backpropagation algorithm, we are having 2 passes, 2 steps. two different phases. One phase we call the forward step or forward phase, and second we call the backward phase, backward step. In the forward step or forward calculation, the input is multiplied by the synaptic weights. What the output at the hidden layers, they are working as an input to the next layer, multiplied by synaptic weights, summed at the next layer, working as an input to the next layer. So multiple times this happening until unless it reach to the output layer. And at output layer, error is calculated. How the error is calculated? That whatever the desired response represented by the training data, supervised manner training data D, and what is the actual response represented by Y. So D minus Y is the instantaneous error. And what is the summed that particular value? We need to minimize it. And that error is propagated in the backward direction in such a way that we modify the synaptic weights so that the error is minimized. And that is why the name of the algorithm is back propagation. That error is propagating in the backward direction. So let us understand how this is happening. So this n in the bracket I am using as a nth iteration. So this is an iterative algorithm. That means we start with some random weights or all zero weights. Generally, we start with the all synaptic weights and passage as random, and we need to modify in an iterative way with objective that to error is a below a tolerance limit. Right. So what is the error at a particular iteration at jth neuron of the output layer? That is the desired response. What the we want to achieve by the neural network at the particular iteration minus what the actual response of the neuron. Right. And similarly, how many number of neurons? Let C number of classes. So corresponding to all the neurons, what this error is squared and summed. So that we call summed square error. Sometimes when the batch mode of processing happening, we can have average error also corresponding to n number of iterations corresponding to size of the training data, right? So these are sometimes termed as cost function, loss function, error functions. And our objective is to minimize these errors with respect to number of iterations. So how to modify the synaptic weight? That is the learning process. So very simple. The first order Taylor series approximation tells that the weight modification delta WJI, that is the jth neuron connected with the ith input, should be proportional to del E upon del WJI, that is the first order derivative of error with respect to, this is the summed square error derivative with respect to its a synaptic weight WJI. And there is a term which we call learning rate. So to avoid the uh, oscillation, we use eta less than 1, usually 0.8, 0.85, and that should be the negative direction. Negative value means what is the error derivative? It should be in the descent direction, steepest descent way by a term eta and proportional to del E upon del WJI. When we do the computer simulation, this derivative is not can be implemented directly in this particular form. So we have to derive. So I'm not going to the derivation part. I'm just telling you that with the help of chain rule, if we apply that del E upon del Vj, which we call another terminology, the local gradient, which is basically a term proportional to this particular neuron itself. So that we term local gradient of jth neuron. Delta j is equal to minus first order derivative of error with respect to its net input at nth iteration. So applying the chain rule and as a function of, as a direct function of the error, say for example, capital E is a direct function of small e and small e is a direct function of y, because desired response is independent of uh, the derivative. So basically this particular term minus 1, this particular term is the derivative of the activation function. So using the chain rule, we can find out that local gradient is equal to error of the neuron multiplied by first order derivative of the activation function of the neuron. Right? This is very important. Error of the neuron and first order derivative of the activation function. So this is the calculation at the output layer neuron, because error can only be calculated directly at the output layer neuron. It cannot be calculated at hidden layer because desired response is not given at the hidden layer. So obviously we have to think of the local gradient for hidden layer neuron. And for hidden layer neuron, uh, if we do in the same way and the derivation, and we find out that it is proportional to the local gradient of output layer neuron multiplied by what does their interconnection strength, synaptic weight, right? So let me do in a summarized way that local gradient of hidden layer neuron is equal to the derivative of activation function multiplied by summation of local gradient of output layer neuron multiplied by their synaptic weight, their synaptic strength, synaptic weight, right? For example, error is calculated at the output layer neuron E1, EK, EM, and what is the derivative of the activation function there? Phi dash with respect to V1, phi dash of with respect to Vk, and phi dash with respect to Vm. So that gives the delta n1, delta k, delta n, that is E1 multiplied by derivative, E1 Ek multiplied by derivative of the activation function, that is the delta k. Similarly, delta m, the Em error at the mth neuron at the output layer multiplied by its first order derivative of the activation function, that is the delta n. Now, delta m multiplied by this synaptic strength, synaptic weight, and summed, that will give you delta j after multiplying its synaptic weight first order derivative, its activation function first order derivative. So in the back propagation, we do the forward pass to find out the error at the output layer. Let me tell you by another diagram. In this particular diagram, I am showing you that there are three input x1, x2, x3, and there are only two layers, one hidden layer and one output layer, which are the processing layers, right? So in the forward pass, what we do, x1 multiplied by the synaptic weight W11, x2 multiplied by W12, x3 multiplied by W13, and bias also summed, that will be the V1, right? Similarly, V2 and V3 are calculated. Now, V1, V2, V3 will work as a input to the next layer after applying the activation function. So, phi of V1, phi of V2, and phi of V3. Superscript 1 is used to represent as the output of the first layer, first processing layer, which is the hidden layer here. And that is giving you Y1, Y2, Y3 of the first processing layer. That is the output of the hidden layer, which is working as an input to the next layer, which is the output layer here. So Y1 multiplied by this W11, Y2 multiplied by W12, Y3 multiplied by W13 will, along with bias B of the second layer, that will be the V1. Similarly, V2 and V3. After applying activation function, it is giving O1, O2, and O3. Subtracted from D1, D2, D3 respectively will give you the error E1, E2, and E3. And after getting E1, E2, E3, we need to calculate local gradients. So what are the local gradients at output layer neuron? Delta 1 superscript 2, delta 2 superscript 2, delta 3 superscript 2. That is the local gradient of these three neurons, which are the output layer neurons, right? And with the help of delta 1, delta 2, delta 3 superscript 2, we need to calculate local gradient of hidden layer neurons by feeding this local gradient in the backward direction. So how they are feeding in the backward direction? Delta 1 multiplied by this synaptic weight, delta 2 multiplied by this synaptic weight, delta 3 multiplied by this particular synaptic weight, right? And apply, first order derivative of the activation function at this particular layer will give you delta 1. Similarly, delta 2 and delta 3 of this layer. Once the local gradients are calculated by multiplying the input to that particular neuron, we find out what is the weight modification, right? And question may arise that how we find out the derivative of the activation function. So when it is a log sigmoid activation function, if we look carefully, the log sigmoid activation function first order derivative can be obtained in terms of feed, can be obtained in terms of the output of the neuron. So if jth neuron output is yj, so the first order derivative is basically yj into 1 minus yj, where and a is the slope component of the log sigmoid activation function. This is the case for log sigmoid. And if it is tan sigmoid, we have the first order derivative different, 1 minus yj square. So generally we use log sigmoid or tan sigmoid, and first order derivative can be obtained in terms of its what you call actual output. So local gradient can be now directly computed. So first it will be calculated at the output layer neuron, error multiplied by the derivative, and at the forward pass we have calculated yj. So that means now we are able to calculate the local gradient. Once local gradient is calculated of the output layer neuron, the local gradient of hidden layer neuron can be calculated in terms of the local gradient of output layer neuron. And after calculating the local gradients multiplied by input learning rate, we get the weight modification. So after modifying the weight, we do again the next iteration. So in the next iteration, again two passes, forward pass, weight, forward pass, that means multiplying the synaptic weight and out the input, we get the output, and at the output layer we calculate the error. If error is below a tolerance limit, stop it. Otherwise this process will continue, weight modification will continue. That is the basically the learning process. So the learning process continues, and till the maximum number of iteration or error is below a tolerance limit. So can it learn any non-linear problem without any problem? No. There are some problems of the iterative learning algorithms. Some of the problems, like it can stuck at local minima, or it can not be appropriately trained within the particular number of iteration. It can stall at, because it is starting with the random weights. So at one time of training, one set of training, it may not converge. You have to again retrain. And so there are number of again problems. Another problem that if we are increasing the more number of hidden layers, the number of computations will grow exponentially. So what are the solutions? So some solutions, like it can how uh, what you call, we can apply some modification of this back propagation, and there are some variants, like uh, one variant is known as with momentum. So back propagation with momentum, we add a term proportional to last time weight modification by a variant alpha multiplied by w delta w ji at n minus 1th iteration. So that we call the momentum. Or we can make the learning rate also to be adaptive. Eta to be adaptive. That means in this particular equation, eta is fixed. Eta is fixed at for all the iterations. In some implementation, to solve the problem of what you call local minima, etc., the learning rate is also and also to make convergence faster, learning rate has been made adaptive. That means eta learning rate at different iteration is different. That is, eta is also a function of n, right? So that we call adaptive learning rate. Momentum terms can also be adaptive. That is basically the meaning of ADAM. ADAM optimizer mostly people are using in the libraries. That is the ADAM optimizer, adaptive momentum. Momentum can also be adaptive. Not only this type of heuristic solutions, heuristic modification in steepest descent backpropagation, there are some solutions which are based on the second order approximation of Taylor series, because the backpropagation is basically the first order approximation. If we add second order approximation, second order term also, second order derivative, the number of computation even very high, and sometimes we get out of memory problem in implementation. There is another way of solution. We can go with non-iterative learning algorithms, one shot training, which we call. So in one shot training, in place of doing this iterative way modification, we can work with, uh, say for example, one algorithm given by GB Huang. It is called extreme learning machine, in which this synaptic weights which are between input layer and hidden layer are randomly assigned. So they are the random numbers. And activation function here is a non-linear. The activation function at output layer is a linear one. So after getting the random weights and biases which are not being learned, the hidden layer output are calculated by applying the activation function at this particular hidden layer. So which in the terms of what you call extreme learning machine, the output of hidden layer is basically vector of synaptic weight Wi ith neuron multiplied by input plus bias and activation function G. So that is the output of the hidden layer neuron. So similarly, all the output of the hidden layer are uh, stacked together, and that will make a matrix. And that are the output of the hidden layer neuron multiplied by output weights beta, which are not known yet. So that is equal to the output of the this extreme learning machine neural network, which is basically single hidden layer feed forward neural network, OJ, right? So if we do this processing, OJ equal to TJ, so the learning actually happens for all the training data. And if we represent in the matrix form, okay, where H is basically the output of hidden layer neuron for all training data, this is a matrix of what is the dimension? It will be of dimension how many number of training observation, that is the number of columns, and how many number of neurons in the hidden layer, that is the number of rows, right? And beta, which has not been calculated, can be obtained by the solution of linear system H inverse T. Because H is not a square matrix, so we need a calculation with the help of pseudo inverse. Okay, so beta can be approximated by the pseudo inverse multiplied by what is the desired response. And hidden layer weights connected with the input layer has been given random. Beta has been calculated by the pseudo inverse method. So all the weights are calculated. That means it is one shot training. And on many problems, this is giving good performance. Another variant, in place of random weights, the weights between input and hidden layer can be obtained with the help of training data itself. So there is no problem of random weight assignment, no non-deterministic performance. It is a deterministic performance. That is the name given is deterministic learning machine, right? So how the weights are calculated from the training data itself. So that is basically trying to make a basis vector. What is the training data P transpose divided by the norm of the training data, and that is the weight matrix between input layer to the hidden layer. And output weights and biases are calculated in the same way as done in the case of ELM by the help of pseudo inverse. Okay, so that is basically deterministic learning machine. Again, it is a better than the ELM. There are even these two models are limited for one hidden layer. They were further modified for multi layer problems. Along with this, because they are given for they are given for the fully connected feed forward neural network, multi-layer feed forward neural network, and the number of weights and biases calculation will go very high if the dimension of input is very high. So this is the limitation of multi-layer feed forward neural network. Say for example, in this I have shown you that if the input is 64 by 64 grayscale image, okay, so the image is represented by 4096 values, right? And 500 neurons. So how many number of weights are there? Basically 2 into 10 power 6 approximately number of weights to be calculated. It is a fully connected, right? And if the image dimension has been increased and it is directly connected to the neural network, again the number of bits will increase. Say for example, it is 64 by 64, and if it is increase, uh, say for example 1000 rows, 1000 column image approximately. So that is, and in the hidden layer that is approximately 1000 neurons. So it is 10 to the power 9 number of weight approximately we need to calculate. And again, it is a high computation task required. So what is the solution of this? Another problem with the existing the models which I have just explained you, that they are taking input in a one-dimensional vector. Okay, so one-dimensional vector, although the information being given as a, if it is an image, it is a basically what you call 2D data, two-dimensional. So that is also a problem, and these problems are solved with the help of CNN, convolutional neural network, in which input is given as a two-dimensional matrix, or if it is a color, three-dimensional matrix, three planes of the 2D matrices, right? And this was the origination of the CNN. It was started in 1989, and along with the ImageNet competition challenge, it goes exponential and growth. And nowadays we have a lot of CNN models which are pre-trained models on a one particular data set which we call ImageNet. So ImageNet is basically a challenge in which there are 50,000 images are used for the training purpose, and 10,000 images has been used for the testing purpose for the category of 1000 categories, 1000 categories. So very first competition was in 2010, and then in 2012 AlexNet was the first winner, then VGGNet, GoogleNet, ResNet, etc. And they are basically trained on a high computation system comprising multiple number of GPUs, right? So with the help of the processing which we need for the CNN models, multiple number of feature abstractions. So mainly when we talk about the deep neural networks, we mean that we are doing the feature abstraction simultaneously along with the classification task, which were in the conventional neural networks were done separately, that classification by the neural network and feature abstraction by manual, so handcrafted features. Whereas in the deep neural networks, with the help of CNNs convolution operation, it is doing feature abstraction automatically, right? So how it is doing feature abstraction, let us understand by just simple, and how it is doing weight sharing also. So let us have this particular image which is of dimension, let in this particular one 5 cross 5 image, and there is a mask of size 3 cross 3. So mask will start from first one, first particular part where it is comprising completely with the mask, and then multiplied and summed. So summed value will replace the center one. Then it will go to the next pixel, same process happening, summed value replacing the center one, and this is going on the complete image. So this the mask basically is the synaptic weights basically of the neural network, and which are being learned through the back propagation. So for the complete processing, only this, in this example, how many weights are being learned? 9 weights to be learned. In place of it is a fully connected neural network and flattened and connected to the uh, fully connected neural network, we need how many? 25. So in place of 25 in this particular diagram, I am trying to explain you that it's a type of weight sharing with the help of only 9 coefficients, 9 weights, right? Is it clear? Hope so.
Yes, sir, it's clear.
Okay. So in deep neural networks, yes, something, some doubt, please ask. Don't hesitate. Okay.
No,
So,
sir, please continue.
okay. So in deep neural networks, not only this type of processing happening by only one particular set of masks, it is having multiple such type of mass, multiple such type of filters. Say for example, it is 3 cross 3 by 4. That means there are 4 such type of filters are used to abstract the features. So we say that multiple number of layers together, multiple number of such type of filtering happening at one particular convolution layer. Say for example 3 cross 3 by 4. So that image is converted into feature vector of how many dimension? Input, if it is not quite higher than the size of the mass, so approximately same size of the mass image, multiplied by how many number of such filters are applied. So if it is image is m by m, so now it is m by m into 4. And then there is some non-linear activation function, which is a rectified linear unit applied, which is a very simple modification of linear activation function, that is greater than x, v greater than or equal to 0, y is equal to v, and v less than 0, y is equal to 0. I will show you by this diagram. Okay, afterward slide I am having. Due to time constraints, I keep some. And because of multiple number of such images generated, we need some dimension reduction, and that is done with the help of pooling. So such type of convolution, ReLU and pooling are stacked multiple times in the deep neural networks, right? So let me explain this concept by an example. So the task of the example is to categorize the input of category X or O. So input X is represented by the value at the diagonals, two diagonals by 1, and rest all the values are 0 or -1, basically in the binary bipolar representation. So blacks are representing -1 and whites are representing 1. So what is the size of this image? Basically this is a size of 9 by 9, right? 9 rows, 9 columns. And on it can be or X type or it can be OR. So how this is happening in the case of convolutional neural network, let us understand. So if it is a very simple, this type of X without any degradation, without any noise, without any modification, without any alteration, it's a very simple to classify the neural network, that is this particular is X or this particular is O. But if there is some scaling, some twist, some shifting, some sharing happens, so it is not able to classify, because say for example, is it similar? Because the diagonals are having 1 1 1, and in this diagonals are not exactly 1. This particular component is 1, but there are same number of ones, same number of -1, but they are misplaced, they are shifted one. So it is not making same, it is not saying that they are both are same. So how to do this comparison with the help of convolutional neural network? How this is helpful? Because it is doing in the small chunks, so it is easy to compare. Let us see how doing in the small chunks. So in the center 3 cross 3, center one, if it is compared, so both are same. And the diagonals also shifted position. If I find out there are 2 by 2 matrix which are same at this position, this place also same, this place also same, and so they are same, but only the position has been shifted. So that can be extracted with the help of small size mass. So that is the reason that the mass are small than the complete image size, right? So let us see how this convolution is obtained with the multiple number of such type of mass, multiple such types of filters. So one filter I am having one diagonal having value 1 1 1 and rest are -1. This particular is having all 1 in the diagonal and the center, and rest 4 places are -1, and this again a diagonal. So what are the values corresponding to this? That is a convolution happening. So let us see what is the way of convolution happening. So convolution is nothing but the multiplication of the mask with the image. So 1 multiplied by 1, that is equal to 1, -1 multiplied by -1, that is equal to again 1, Similarly, for all this 9 position, if it is multiplied by the same mask 1, and all the values will be say 1, right? So you are able to understand that how the convolution is happening. This particular mask coefficients are multiplied by the image value, and that is all 9, right? The values to be normalized. So how many number of coefficients in the mass? That is 9. So the complete is divided by 9, and that is the center value to be replaced. So this center value, although it was 1, in the output also it is 1. So that is the convolved value. If it is same, so maximum convolution value is 1. What happen if it is matching on the different position? So it will not be 1, it will have a different. Say for example, this particular the filter which is not same as the center one, so what the convolved value? So it will be slight different, because at some places -1 multiplied by 1, that is equal to -1, and some places it is matching, so that is equal to 1. So total value in place of 9, now we are getting 7. So 7 divided by 9, that is equal to 0.55. So center 1 is basically replaced by, in place of 1, that is equal to 0.55. So similarly, for this particular mask convolved on the complete image, will get the values maximum 1, and some places negative, which are just opposite of the direction, and some places between negative to 1. So minimum value we can get -1, and maximum value we can get 1. Similarly, the operation has been done, not only this particular mask, has been done by the other mask also. So that is, one image is represented as a stack of filtered 3 images, right? So obviously different filters has been applied, so different values has been obtained. So that is, the one image becomes a stack of filtered image, right? Now that, because the image was of dimension, say for example m by m, say for example in general we have the images 256 by 256 of some sufficient information, not only not a very high size of images. 256 by 256 is sufficient enough to convey the information, and that is replicated multiple times. As many number of filters has been applied, so we need some dimension reduction, and that dimension reduction by done with the help of again a pooling operation. That is a very simple operation, which basically a stride of 2 or stride of 3, and window size basically either 2 by 2 or 3 by 3. So there are two type of pooling operation: max pooling and mean pooling. Max pooling means what is the window has been considered, out of that window what is the maximum value, will replace this particular complete 2 by 2 matrix. So in place of 2 by 2, I am representing this by one value. So this 9 cross 9, sorry, before this it was 9 cross 9, and after filtering it becomes whatever the padding has been removed. So this becomes 7 by 7. Now after pooling it becomes 4 by 4, right? So this particular 2 by 2 window has been replaced by one value, max value. If it is a mean value, yes, yes, please speak again. Okay, let me. So that is the way pooling happens. So in this particular window, that particular, what is the max value, 0.33, that is replacing this 4 by 4 matrix, and so on. So that is the way this complete 3 filtered stack of the images now converted into small images. Now, what is the meaning of value? I was telling earlier that if it is positive, the same value. If it is negative, that is replaced by 0. So 0.77 same as minus 0.01 replaced by 0, and so on. So now after applying the rectified linear non-linear activation function, this image is converted all positive. Negative value has been replaced by 0. So that is the way of processing of convolution, ReLU, and pooling. So this one image is convolved, activation function, and pooled. So that is the stack of the image. Now such type of processing repeated many times, so that is the stack of such type of layers. And if I do two stacks of such, I am getting this particular output image. And now it is flattened and given to fully connected neural network. So by finding the value, what is the maximum voted value? So that is 0.92 if it is X, and corresponding to O, it will have a smaller value. So what is the maximum value? That is signifying the category of the input, right? So that is the way of working of convolutional neural network. Uh, Convolutional neural networks not only many variants are there. As I told you, in the evolution of the convolutional neural network, there are many variants: AlexNet, ResNet, GoogleNet, etc., etc. And all these have been applied in many of the healthcare applications like COVID detection, X-ray scanning, CT scan imaging, etc., etc., blood cancer diagnosis, leukemia diagnosis, etc. So basically, in the most of the cases, the uh, healthcare applications, the classification has been done with the help of some images. The images are representing either the category of, say for example, here I am showing you some data sets, categories of, say for example, COVID. So this particular COVID chest X-ray images containing 5856 images, and 5856 images are categorized in two categories: COVID and non-COVID. Because COVID images are more, so the size of 4273 images are classifying to one particular category, and normal images are 1583. So these can be divided into two set, training set and test set, and then these types of algorithms can be applied to classify them in what you call uh, healthy or COVID one. Not only this, there are some more types of images, types of data sets. Some I am, let me, uh, I, I would like to show you some images. Okay. So how this processing happens, we take the image, we do some types of processing. If the images are not of good quality, we do some contrast stretching, histogram equalization, or some filtering type of operation, then divide into training set and test set. And then we can use the pre-trained data set for feature abstraction. Then feature vectors can be given to like ELM classifier, DLM classifier, and then that can classify the images into normal and COVID, or whatever the type of, say, blood cancer images. So that can be the same way, cancerous or normal images, normal category of the images. So that is the application of what you call this neural networks has been applied in many types of health diagnosis systems, right? So with this, I am concluding. Uh, if you have any doubt, you can ask, or yes, any doubt, any question?
Participants, you can ask your questions now. And I would also like to request all the participants to please turn on the camera and allow me to capture this moment with the esteemed speaker.
So I have a query.
Yeah.
Sir, as you told, CNN can be only applied for image data set. Whether can it be applied for some categorical data also?
See, what the example I have taken, that is the images has been used as input to the neural network. So not only the CNN can be applied for 2D data or 3D data as an image, they can be applied for 1D data also. Say for example, ECG signal analysis. So EEG signal as a 1D, and there the convolution is operated in one dimensional, 1D convolution basically applied. You understand? 1D convolution. Signal processing concepts, probably you may be aware. Convolution is basically the concept of signal processing applied in the neural network pattern recognition, right?
Okay, sir. Like heart disease data set.
Yeah, hard disease dataset. What type of dataset you are talking? Is it
It has.
ECG signal? Yeah, ECG signal analysis has been done with the help of 1D convolution, and obviously it can be applied.
Okay, sir.
but CNNs are mostly popular because of it's a 2D processing, because the information represented in 2D form, and that information to be extracted with the help of 2D convolution is very powerful tool for extracting the 2D information, actually, which cannot be extracted with the help of 1D convolution. So that is the what you call motivation behind the 2D processing, although it can be used for 1D processing. Anything else? Any other audience?
Thank you, sir. We sincerely appreciate the time and effort you dedicated in delivering such an engaging and informative session on artificial neural networks. Your clear explanations of their workings, advancements, and the challenges they address were really helpful. The way you broke down some really complex topics and highlighted key concepts made the session not only educational but also inspiring for all of us. Thank you for an enriching learning experience, sir.
Most welcome. Although the topic is very broader, very lot of things are there, uh, but I touched some component which can motivate you for further research. Actually, that is the basic objective of this presentation.
Yes, sir. Thank you so much.
Okay, welcome. So, anything else, or should I leave now? Okay. So, see you some again other time. Okay, bye.
Thank you, sir.
Okay, welcome. Bye.
Okay. Now we will have a break for 5 minutes and we'll join again for the next session and the final session.